identity by descent.
Good. Yeah, so thanks very much. Oh, okay. The organizers for inviting me, and this being a mathematical place, I thought it would be good to talk about something that was slightly more theoretical amongst the things that have been going on in my group. And at the time of the invitation, I thought that assembly was important, and there were some interesting results about new assembly approaches that Jared Simpson in my group had been working on. And I still think assembly is important. But in the meantime, Kelly Harris, who's been an MPhil student the last year, has completed some very nice work, I think, about the relationship between identity by descent and identity by state in under a coalescent model. And I think that's actually it's quite informative about imputation processes. And as we go to sequencing panels of individuals and then trying to use that information for inference on other individuals, I think these are going to be progressively more important approaches. So I thought this was a good opportunity to talk about her work. And in a way it's relevant, I guess, to the next session, so it's not too far off this morning's topics. So these are basically Kelly's slides about this. Okay, so what's the motivation? Well, in genome-wide association studies, which have been an extremely powerful tool for human genetics in the last 5 years or so, your genotype only had a subset of the markers that are variable, and they act as proxies for unobserved causal variants. It may be, that one of the things the genotype is actually the causal variant, but often it's not. And that works because there's linkage disequilibrium, which locally, so that variants locally are correlated. And in a sort of naive test, just the straight correlation is what matters, the R squared value. But that isn't really making an optimal use of the information that you have available, because there's more structure there, and the structure of correlation arises because you have shared pieces of chromosome which two individuals have both inherited from a common ancestor. And so we're going to look into that structure, and particularly what underlies imputation. And I'm going to draw a picture, this being a maths place. And I think I'm going to draw it over here. So if you've got two copies of the genome, there'll be some and we look at where they're different from each other. Might be different at those positions. So there's going to be regions which look identical. We call them identical by state. And if we look at why, and the reason, the places where they're different, and those are differences, and those will tend to cluster. So we'll get long regions of identity by state and sort of clusters of differences. And the reason for that is that these two regions of the genome will share a common ancestor, and if that common ancestor is recent, then there's not much time for there to be a mutation, and so mutations are relatively rare. So between these two, that difference here between these two copies is because at some point since the last common ancestor there was a mutation on one branch. Now over here, where there's maybe more differences, the common ancestor might be further back in time. So I'm drawing time on this axis, and this axis is the genome. Okay, so we're going to have regions of the genome, and in fact, if you take two copies, the time back to the common ancestor is a piecewise constant function. So they're blocks that are shared, in fact, from a single common ancestor at some point in the past at time t1, and then if we go this way, there may be another period here, and that might be t2, and we've got a couple of mutations there. Okay, so regions that have been shared from a common ancestor without recombination are identical by descent. That's our formal definition here of identical by descent. And what are we going to say here? So there's a big variation. Some of these times might be just 10,000 years ago, some might be 1,000,000 years ago. That's a factor of 100. And effectively, the rate at which you see variance will be 100 times higher in the old sections than the new sections. And because on average, if we assume even recombination, mutation rates and recombination rates, which is not true, we know that they vary, but then you'd expect Poisson number of mutations per identity by descent region, which is constant. So if you get a long region, then they really are very nearly identical. There'll be of identity by descent, but there will be some, there's chances of some differences there. Okay, so this is essentially the basis of imputation. What you're doing with imputation is that you find a region in which it looks like you're only observing a subset of the markers, but at those markers that you observe, the two sequences seem identical. So you make an inference. Okay, it looks like these two sequences, this sequence that I've got as my test sequence and a reference sequence, look identical over a long region of, say, several hundred kilobases or a megabase. I'm going to presume that they're actually identical by descent, and that they're identical the whole way across that. And then any information I have about the reference sequence, I can copy across to my test sequence. So you can have a reference panel where you have dense information about the genetic state. You might have the complete sequence now with the 1,000 Genomes project and full genome sequencing. And you have a test individual where you might have just genotype data at sparse loci. So imputation is basically a process of going from IBS sparse to an inference of IBD to an inference of IBS dense. And what we're wanting to evaluate is how confident can you be in each of these steps under a model. So we have quite good models for this process, statistical models based on coalescent theory. Are the assumptions made by this set of inferences that we're making of arrows valid? With what probability, if we see sparse IBS over some length L, how confident can we be that they actually were IBD? And then, given that they're IBD, then we can know quite a lot about actually what the chance is that they're really IBS densely. Okay. So, IBS, people actually often talk about finding a match across a megabase or something, and therefore inferring that and saying that, oh, these sequences are IBD. But actually, that's not really true. All you can do is all you can observe is IBS. You can only observe identity by state at some set of markers. You can't actually observe the history of what the ancestor looks like and where the recombination events happened. You have to infer those things. In linkage analysis, this is also true. In fact, this is the basis of linkage analysis. One infers IBD given IBS, but there's a lot of pedigree structure. There's a very strong prior structure that constrains things, and so you can make extremely strong inference about this step here from IBS to IBD. But even in various linkage situations, there's a certain amount of uncertainty in this, and there's been a lot of work put into modeling that process. But if we're thinking about applying this in a sort of case where we don't have any pedigree history, then things are actually much freer, and we fall back on coalescent theory. Okay, so how are we going to work? We're going to work with the standard neutral coalescent. Well, I'll adjust that slightly in a minute, but the basic model is the neutral coalescent with recombination, random mating, constant effective population size. In fact, one can do the calculations with any piecewise constant effective population size. So we can look at different population histories with bottlenecks and so on, and we'll come to that later when we look at some real data fitting to real genome sequences. And for now, there are no recombination hotspots, certainly no selection. That would make things hard. Recombination hotspots one could model as well just by putting them in essentially to the calculations. So it's not a hard thing to put. So we've got mutations per site per 2 generations and so on. And it turns out, if we think of what we're interested in is the probability of IBD given IBS, that's the probability of IBD and IBS divided by the probability of IBS. Probability of IBD and IBS is a very easy to calculate thing. It's the probability that you've got some region here that's of length L, so it's all conditional on length, and there are no mutations and no recombinations in that. And you can think of those both as sort of events that could happen, and so it's just a simple formula. So what's hard about this then? If that's easy, the hard bit is the probability of IBS. It's the probability, because you can get IBS, and in fact it happened here, the IBS region extended beyond the IBD region, so there was a recombination event, but it just happened that there were no mutations taking place. So you can have some complicated history of recombination and still get IBS. And that's the thing that's harder to calculate. L is the length of the region which appears to be IBS. Yes, which we're considering.
What's the feature of the data?
What's the what?
It's a feature of the data.
Yes. We're going to condition on there being IBS and length L, and we're going to ask, is this also IBD? We've got a piece of... So in the case where we've just got 2 sequences, and we're batching them like this, we can do this calculation using the sequentially Markovian approximation to the coalescent, which Gil McVeigh and Niall Carden introduced a few years ago now. Because we can think of this sort of Markov process running from left to right, at which the true state changes from coalescence at some time t1 to some time t2. There's a Markov chance of doing that. That jump probability is different depending upon the time. If you're at recent times, then probability of jumping is low. And we know also about the distribution of where you're likely to jump to. And so we can do this calculation. It has to be a numerical integration essentially of that, but it's quite a straightforward thing to do. And the good news here, the top line in a sort of simple case is, this is 10,000, 20,000, 30,000, 40,000, 50,000. If you assume a mutation rate of twice the recombination rate, or 2.5 times, then if you start seeing a decent length of shared haplotype, you're actually pretty confident about IBD. The grey curve, though, is a little different. That's saying you're not really imputing. If you actually have the complete sequence, then you can find these matches. That's all very well, but you're not making any inference. So what does imputation refer to? Well, it refers to looking only at a subset of sites. And the way we modeled that is we didn't want to model the whole ascertainment process of how SNPs are chosen to go on genotype chips. So we modeled the case where you're only observing a tenth of the variant sites, where basically the mutation rate is a tenth of the normal mutation rate. That would correspond to seeing a het between 2 sequences on average every 10,000 bases, say. Because true hets every 1,000 bases. So this is like saying in genotype data from a 1 million SNP chip, for people who think about these things, you get a het observed about every 10 kb, which I think is probably a reasonable kind of model density for the information density. In that situation, if you see some interval that's free of differences at this lower mutation rate, what's the chance that things are IBD? Well, it's much lower. This is at 35%, the short regions, around 10,000 bases. Of course, in 10,000 bases, this observation, it's quite likely you don't see a difference at all. So it's sort of uninformative. But it's only going up quite gradually. And I'm going to show it turns out that's still, you have to get to hundreds of thousands of bases to start to get high confidence that if you've got a single match, then things are, that you've got IBD given IBS. So that's one issue, not seeing full data, which is of course the situation you want to be in. The second problem is that normally one is actually looking at diploid sequences, and this is haploid sequences. So in a diploid sequence, I guess people over there can't see this, but maybe I'll draw it here. You've got a diploid sequence, and you're matching to a panel. Let's say it's a panel of reference haplotypes. So then we've got a haplotype, and we've got a block here, and it looks like this diploid sequence is matching that. Well, one possibility is that one of the haplotypes is matching this one. That would be kind of good. That would fit what we want. But an equally, or not equally likely, it depends. We're going to have to calculate it. Another possibility is that the first half, one of the haplotypes is IBS for one part, and the other haplotype is IBS for another part. So that, in fact, there's no IBS segment even in this diploid individual that matches the single reference haplotype, let alone being an IBD, there being an IBD segment. So we can talk about the apparent IBS between a diploid sequence and a reference sequence, as I think it's been referred to before as IBS is greater than or equal to 1. And we can calculate what the probability is of observing that. And then again, we can calculate what the probability is of what we want, that there's an IBS segment and that extends the whole length, and that one of the haplotypes is IBD with the parent. Actually, that you share one of the two haplotypes IBD. So this is a slightly more difficult calculation, because rather than just having two sequences, we've now got three sequences, and there's a tree that relates these in time. And the state in the sequentially Markovian coalescent is now not just a single time, it's a tree with essentially two different times, two different coalescence times in it. And Kelly could, I think, do that calculation in the very limited sort of case, but came up with an approximation in the sorts of cases of interest to us that we could probably go to afterwards, given the time. But basically, kind of, there's one particular tree, the one that matches your assumptions, which is much more likely. You don't want to put all the density on that tree, but you can make this sort of assumption that you're falling back onto that tree when it. Let's see. You don't have to keep track of all the different tree transitions, essentially. Or one can approximate by collapsing some of the tree transitions into one, and that reduces the size of the space, and that makes it computable. Okay, so having said that, here's a plot of against alignment length time. This is now 200,000, 400,000, 600,000, 800,000. That's a megabase. This is the sort of the tool for mathematicians. That was the haploid case we considered before, where you had full information. This is the haploid case where you have a 10th density information. So you can see once you get up to 500 kb, then you can have quite high confidence. That's the diploid case with full information. The black squares are the full correct calculation. The white things are the approximation. And this is the diploid case where you have partial information. And this is actually what's relevant to imputation. You have a diploid sequence with genotypes at a sparse set of positions. And there, if you have 500,000 base match, it looks like you've got a 500,000 bases long, where you're matching into the reference sequence exactly at a tenth of the sites. Then there's only a 70% chance that you've got an IBD haplotype there, from which you could make inferences. So that looks pretty bad. I mean, even getting up to 1 million, you're getting up to 85%, but it's sort of flattening out. And actually, Augie, who's working out here, we'll hear about it a bit later. It's not as close to one as you might really want. So when we rescue this situation, well, luckily we can. So it turns out that the case I drew here doesn't happen all that. It's actually not that much chance that you have two equally sized things. The things that happens more often is that you get, there's an IB, that there's a little piece at the end, basically, which is different. So, and we've been quite strict so far. We've been wanting to say, this whole region is IBS, what's the chance that the whole region is also IBD? And you might say, well, actually, what our expectation is that it'll be the chance it'll be IBD is very high in the middle and maybe drops off at the edges. So can we ignore some fraction at the end, which I think we're going to call x for now, and just look at a section that's L in the middle and it's flanked by two more sections of size x? Okay. And yes, that's good. So this is the curve you had before. If you add 10,000 bases onto the end as kind of flanking stuff, then you don't make much difference. But if you add 50,000 on, then things start to get better. And once you add 100,000 bases onto each side, if you have a match which is 400,000 bases with 100,000 bases of flanking sequence, so 600,000 bases in total, the middle of 400,000 bases is IBD with quite high chance, with 90% chance. So basically when you're doing imputation, and in fact I would argue what's going on in things like impute and MAC and all these impute programs is they're finding these long shared segments, they're copying off them, and they tend to recombine onto another, switch to another segment, not right at the end of the IBS region, but somewhere a little in, because there's some chance of, there's an overlapping one and you'll flip before you get to the end by standard chance. Of course, they're doing more complicated things as well in terms of averaging across multiple cases. So what, can we make some, can we actually make some proposals about what the consequences of this are for imputation? So we've been calculating, we're actually calculating the full probability of IBS. These are all conditional I've been showing you so far, but we can actually say what's the chance of finding a match in a panel of size 120, 120 haplotypes, or 500 haplotypes, or 1,000 haplotypes, of finding a match that's 500,000 bases long, or 1,000,000 bases long. Are we going to have them? So again, this is all based on the sort of standard neutral model without effective population size variation for the time being, and that is going to matter. But here we have, this is the probability of finding something, a match in a panel of size n, where n is 60, 120, 250, or 1,000. So 120 would be like HapMap, 60 individuals, 120 haplotypes. As a function of distance, of length, what's the chance of finding a match, essentially? And what you can see is that with 120, it does fall off in the range in which you're interested. This is 100,000, and actually these are the flank sizes, I think now. No, is that 1,000,000 bases? That's 500,000 and 1,000,000. So it's not 1, but it's quite high, but it's not 1. There's some fraction of the space we're not covering. And we can convert from that, because we can work out what the probability is. If that was the best that you had, what's the probability? What's the probability of? We can work out what's the how confident could you be in the inference? How confident could you be if you had something of this length, that things were IBD, and then how confident could you be in filling in the missing data? And that's on the next graph. So this is if you want a 0.01% over. What's the chance that you can have 99% confidence? What's the chance you can have 90% confidence? How do I completely turn that off? Okay. So this is again with 60 haplotypes, 120. So once you get up to 1,000 haplotypes, they're saturating essentially. You can have very high imputation confidence. But with 120 haplotypes, even in a standard model, you're only going to have about 70% chance of being 99% confident, or over 70%, according to this sort of simplified model of imputation. And that would be with 120 individuals. So and I think that these are actually, I would argue, consistent with at least my picture of the way the imputation works, and people have been moving to panels that are in the hundreds of individuals and pushing themselves up here in terms of imputation accuracy. So I think I'm sort of running out of time. We've looked at, is this all real? Does this conform to reality? We thought about how to assess this. So And rather than look at imputation, where there are all these ascertainment issues, we looked at individual genome sequences. So this theory applies to runs of homozygosity in individual genome sequences, asking what's the distribution of lengths where you see no observed heterozygote. Okay, the problem there is, and we can ask again, we can sort of thin out to every tenth of a position and say if you find a run of homozygosity which has got, looking at every 10th base, what's the chance then that it's also homozygous at all the intervening bases? The problem we have, so we have a number, 11 human genomes, and we've got all the data, and some from the 1,000 Genomes Project, some from other projects. They've been recalled in a sort of way that is all consistent and equal. There are false positives, and any false positive call breaks all this up, because we're looking for exact matches. So we can fit that. Essentially, there's two curves here. This is the curve we expect under our theory, and the second curve is this white curve, is the curve that you'd expect from false positives, which trails off. This is the distance I'm not going to try and even explain what this is, given the time. But basically, you can fit observed data, which are the white things under here, with the black things, which are a sum of these two. So we have to actually explicitly put in a error rate, and the error rate that appears valid for this case is 2.3 false positives per 100,000 bases, which is actually quite consistent with, it may not be as good as some people would like to think their genome sequences are, but it's not so bad, 1 every 40 kb or so. So given that, this is some data, this is the overall average data across all 11 individuals. This is the actual measurements. So what are we plotting here? We're plotting the ratio of runs of homozygosity to thinned ones. So if you get a thinned run of homozygosity, what's the chance that or how many are there that, essentially what's the chance that it's also homozygous? That's the real data. The white triangles here are the corrections of the real data after we apply this correction for 2.3 errors per 100 kb. And the black is what the theory gives us. So I'd argue that black looks like these white diamonds, more or less. If we split them by population, then these curves are actually different for different populations. And the best, I'm going to quickly run through them. So this is the Europeans. These are 4 different Europeans, I think. 3,000 genomes and 1 cancer normal. And that's the fit. These are the Asians. That's the data. That's the fit up here. That's the European plot. So you can see there's actually quite a lot of difference there. And you can be more confident there, and that's because there's an extra bottleneck more recently, 5,000 years ago, in the Asian model. So the Europeans had a bottleneck about 2,000 generations ago. The Asians were the same until 500 generations ago, and then they had a subsequent bottleneck. And then the Africans are this case. So these are African data. These are corrected African data in gray diamonds. That's the African model. That's the Europeans on the same scale. So they're quite different. You get quite different kinds of behavior. So in conclusion, Kelly's developed, worked through the model, the consequences of the sequentially Markovian coalescent model to talk about, to calculate the probability of IBS for an arbitrary pair of haplotypes, and also for when you have a panel of individuals for the best haplotype in that panel, the best match in it, the longest match in that panel. We can make, we can draw conclusions about how long a match you need in order to be confident of IBD, identity by descent, and therefore make inferences according to the sort of standard imputation inference framework, at least the way I'm casting it. And it suggests that one wants hundreds of individuals, but actually at something like of the order of 1,000 haplotypes, you're beginning to get good accuracy, at least. But on the other hand, that this is very dependent upon population history. And I guess that's going to fit later. We're going to hear that particular population histories with isolates give you much greater power, allow you to work with smaller imputation panels and get higher accuracy. So Thanks so much.